welcome to the last video from chapter 29, and because we've covered chapter 30 earlier in the semester when we talked about planets and then exoplanets, this is actually the last lecture video of our semester. Now, we left off the previous video with this chart showing that we've gotten through a bunch of topics. There's a couple of steps that we skipped, but we've gotten through a bunch of topics that are slowly bringing us toward the edge of current scientific understanding. And for this video, the topics that we're going to cover, inflation, acceleration, and then briefly dark energy, all of those are topics that are difficult to discuss without more physics and math. And so they're topics that we aren't going to put as much weight on for studying and fully processing compared to the other ones that we've talked about in this chapter. So out of the 3 videos from chapter 29, if this video is one that the topics don't quite click with you the way they do for the others, that's okay, and part of it is because we just can't approach these topics with the same rigor that we would otherwise without adding additional physics and math that are beyond the scope of this class. But we're going to do our best, and we're going to make sure that we kind of recognize what these new breakthroughs in modern cosmology are so that we can understand where the ongoing research is in this field of astronomy. Okay, so the textbook itself, this video is covering mostly section 29.6, but we will talk about the philosophical note of 29.7 at the end of this video as well. Okay, so one of our 2 big topics for this video is inflation. Now, inflation is an idea that fixes several problems in cosmology that I didn't even introduce in the previous videos, because I want this to be a sort of standalone topic that if it doesn't quite click, again, don't feel too stressed about that, because these topics are, the 2 in this video are a lot tougher to kind of work into our 1 semester survey course without more math. But inflation refers to a very rapid expansion that happened in the first tiny fraction of a second after the Big Bang, and only lasted for a tiny fraction of a second after the Big Bang. The problems it helps solve have to do with curvature, which we mentioned very briefly in 1 slide in the previous video but didn't talk about, and the horizon problem for the cosmic microwave background. Now, the horizon problem for the cosmic microwave background has to do with the fact that if we look in one direction in our sky, and we think about how the patchiness of the sort of hotter and colder spots on the CMB, that pattern, it's almost identical patchiness to the opposite side of our sky. The reason that that's an issue is because without inflation built into the model, the standard expansion or inflationary, the standard expanding universe model can't account for the fact that those parts of 3-dimensional space could have been in thermal contact. So inflation allows a lot of things to have been closer together than we expected in the past. And the flat curvature thing, we can actually think about using our balloon analogy. If we were on the surface of the balloon and it has this nice curved surface, if it were suddenly inflated by a significant amount, it would look flat to us. In the same way that if we aren't thinking too critically, we might think that the Earth is flat, because if we look to our own horizon, it looks kind of flat because it's big enough. But the ant on the balloon is in fact on a curved surface. It just looks flat to us. And for the inflationary theory, no matter what shape space-time has, if it went through this period of inflation, then it will look flat to us, and it will look like a flat curvature. So again, we don't need to get too far into the details of those problems that the inflation theory is fixing, or even the details of the inflation theory itself, but just recognizing that that's something that it is a theory, which means it fits enough evidence to be boosted to that level, but there still are a number of scientists who think that it will be adjusted or amended even in our lifetimes. The other topic brings us to the fourth of our 4 questions that I posed at the very start of our Chapter 29 set of videos, which is, what is going to happen to the universe? Towards the end of our second of our 3 videos, we had a couple of example possible expansion models for the universe, and we talked about how the Big Crunch has been ruled out, but we haven't really talked about what the correct answer is. And we're at the point in cosmology, in astronomy, where we have a best guess, but we actually don't have a single correct answer for it. However, the details of what we have been able to rule out and what we are thinking about have to do with the fact that the universe is accelerating. And I want to at least walk us through what measurements were made to figure out that the universe was accelerating. Now, the graph here is from the lecture tutorial, from our normal lecture tutorial book, the lecture tutorial Hubble's Law, which is a long enough lecture tutorial that in the online class we don't do it. And for the flipped classroom, it kind of depends on the timing from semester to semester, whether it gets a chance. But what I do want to do is use this to walk us through how we're able to figure out that the universe is accelerating. Now, this graph itself is a velocity versus distance graph. And if we think back to our discussion of Hubble's law, back when we introduced it, we said that Hubble's law indicated that we have a straight line. And that's true if you look at objects that are at nearby or even medium distances, where most of the points, I could probably even draw a better line to go through more of those points, where there's clearly a straight line. The trick is, and on this diagram it's been greatly exaggerated, the trick is if we look at further and further away objects, they have a different slope to their line through those points because of this kind of curved shape. Now, the real trick here is to recognize that as we look at objects further and further away, we're looking further and further back in time. The blue line here is for before, back in time, and the red line is for right now, before and right now. So these really distant galaxies, if we just look at those points, then that shallow slope is telling us that in the past, back then, before, blue line, we had a shallow slope, and so we had slow expansion. Whereas if we only look at the points for right now, right here, red line, it's a steeper slope, which means we have a higher expansion. So it's kind of like if you're on a highway and you look down at your speedometer and it's saying 80 miles per hour, but you know that a minute or two ago you were only going 60, because we know what it was in the past, slower, and what it is now, faster, we know that in the meantime it's been accelerating, that on the highway we've been accelerating, that the expansion rate of the universe went from a slow expansion to a current faster expansion, which means that that expansion rate is accelerating. Now, the explanation for that acceleration is one that we don't have a single correct answer for. One explanation is something that behaves like the cosmological constant in Einstein's models that we haven't talked about because they're detailed physics outside of the scope of what we need for this course. But the sort of placeholder idea for the fact that we know we need something to be pushing back against gravity, that placeholder unknown is called dark energy. It doesn't have anything to do with dark matter, and it really isn't a great name for it. But dark energy is our way to describe the fact that we don't know what this piece of the missing puzzle is, but we know that we need this missing piece to be pushing against gravity. So there's a constant fight between the inward pull of gravity, trying to pull mass together, and the outward push of whatever it is that dark energy happens to be. And when we talk about dark energy, what we're saying is that there's either some substance or more likely some piece of physics that we need to better understand to put into our models to explain things. Now, the drawing here on the left is going through the scale of the universe over a function of time. And what we see is we know where we currently are at. And there's basically two possible fates for the universe. And those two fates, we don't know which one is the correct one for the future without having a better understanding of what dark energy actually is. So early in the universe, when everything was denser, because all the mass and material was packed closer together, gravity was a stronger force. And after inflation, the universe actually slowed down its expansion. But over time, as things expanded, even though they were going slower in that expansion, in the same way that you might be going 80 miles per hour on a highway, you slow down to 60 miles per hour, you're still moving forward. The universe is expanding this whole time, it was just moving forward more slowly. But about 6 billion years ago, dark energy started to be the dominant force. And now it's unclear whether, based on how dark energy actually behaves, whether it will sort of even out to be a single value of how much it's pushing against gravity, or whether it will continue to push more and more against gravity until we experience what would be called the Big Rip. So those are possible future outcomes for our universe. And it's the reason why at the very top of this pyramid, there's a little question mark. Dark energy is still something that we don't fully understand as a scientific community, but there's a lot of people working on trying to build a model that accepts everything and we fully understand. To really make sure we recognize how new these last two steps of the pyramid are, it was observations from the late 90s that actually helped determine that before blue line was a shallower slope than the right now current points in a Hubble's law kind of diagram. So we've been working since those late 90s observations to build into our mental model or our scientific model what could be the cause of that. Now at this point in the pyramid and at this point in the chapter, and possibly at this point in the whole semester, you may have more questions than I have answers. And that really is highlighting what science is. That science is not having a whole bunch of knowledge that we just kind of like lock up in a warehouse. This whole semester, I hope we've realized that science is about figuring out how to think about things, how to take observations and use critical thinking to develop a model, or how to determine whether a model fits observations or not. And a lot of our discussion has gone through some of the historical stories of how we figured out what we did, because it didn't come from just somebody knowing all of the answers right away. So as the sort of pyramid on our slide fades off into the background, there's ongoing exploration, and we don't know I don't know what the future for cosmology, this particular field of astronomy, holds, but it is one of the fields that has seen the most development over the last couple of decades. Now, there's one last philosophical note, a sort of bigger picture idea that I'll leave us with and kind of wrap up our whole semester to think about, and that's the anthropic principle. Now, the anthropic principle is something that a lot of scientists don't really like because it doesn't have a clear physics and math-based model for things. But I actually kind of like it. The anthropic principle says that Okay, there's a lot of factors that if they were slightly different, we wouldn't be here. If the universe were slightly less dense or slightly more dense, if that matter-antimatter imbalance hadn't happened, if the sun were a little bit too much more mass, then the Earth wouldn't have had a chance to develop. But the anthropic principle is mostly on the cosmological side of things. All of these possible knobs that we could turn that allowed our universe to look the way that it does, it's also true that if you changed any of those things, it's very likely life wouldn't have developed on Earth. And so I've been walking around it, but the anthropic principle basically says that the reason the universe has the particular values it does, all of those possible densities, everything else, is because we are here to study it. Because if those values were different, we wouldn't be here. And so some scientists kind of think of it as a cop-out, like why can't we have a really clear scientific explanation for why the universe has flat curvature or the particular amount of dark matter it has or anything else like that. But I kind of like the idea that maybe this has happened in other dimensions, who knows. But like, for example, a lot of you might have been thinking about when are we going to talk about the multiverse? And the problem is the multiverse is not something that we can talk about in a science course because we can't ever test or verify those ideas, which is a really important, absolutely key aspect of science. It doesn't mean that the multiverse idea isn't valid. It means that we can't test it using scientific purposes, and so we can't include it in a scientific course. But the anthropic principle kind of talks about the fact that, hey, if we had an infinite number of different universes, all existing in different dimensions, but infinite in size somehow, that maybe we're in this one asking all these questions because we aren't in all of those others that have slightly different values. So kind of an interesting thought. Okay, we have made it through almost 30 chapters of content. Certainly a lot of those we covered the highlights of, but looking back at our semester, we've learned a whole lot, and I hope that you've enjoyed the ride. I know that I have, and I can answer any questions you have in our normal discussion boards, emails, things like that. And this is it. So, good luck.